I write a compiler for a small programming language, Elna. It is imperative and low-level programming language with minimal design. The language itself looks a lot like Oberon or Pascal, but a bit more simple. And the compiler is written in itself, so I already write the compiler in the language itself, but the language is not finished, so there is still a lot of stuff to do. We do not have error handling and stuff like this, but currently I'm working on the code generation, and I want to change a bit how the 3 address code, so the intermediate representation is converted to the assembly, and this the first assembly that I generate does not use hardware registers, or uses them in a few places but not for normal variables, but it uses special pseudo registers that are later allocated to hardware registers. And my earlier versions of the compiler handled global variables spatially, so the pseudo registers were used only for the local variables but not for the global variables, because global variables need generation of other instructions, and I want to unify it a bit and move variable or loading of the value of a variable to a later stage, so that pseudo registers refer to global and local variables, and only during their allocation pass, so the pass that is done after the assembly generation, so that only this allocation pass distinguishes between local and global variables. This operand value function is just used 3 times, I think. So we begin here, and instead of generating the load address instruction for the static variables, we just generate a move instruction, and we replace it with load address later during the register allocation. And basically I want just to remove this branch, I suppose, then. So the whole thing, and we have to look where it fails then. Or probably we can even begin with a simpler case if we just copy this function temporarily and rename it to something like load operand value 2. I wonder what is the difference between entirely load operand and load operand value. Not load operand, we have also an operand value function which is checks for constant first, and then for a variable, and it loads address. Or generates a pseudo mem. Okay, I see. So this function just always generates also generates a pseudo register as source. And here we generate pseudo mem or pseudo, depending on what is the type of the symbol that we are looking up. Well, so let us take this function and just rename it to something like rtl operand value 2 and try to compile it. And the first case is a call expression, and here we use this function to load a value into a register. So let us replace this call with 2. And this one works already. So then we go to the next case. And here it is the return statement where we put a value into a 0. Oh, of course I haven't changed this to function. So we need to remove this pseudo lookup here first. And we probably do not need this pseudo symbol anymore in these functions, so this one can go. We also do not need variable map now, but we won't change the arguments just yet. So once again, load operand value and load operand value 2. We begin with the return statement, because I hope that I do not return any global variables, so that this could just work. Yes. And the second case will probably break. Now at least we know what generates wrong code. Let us generate here also a debugging instruction, so that we can look into in the assembly. Where do we have this stuff? What we write in the debugging instruction? In a list append. I print the first two arguments. We can just ignore the arguments for now and just set them. Now RTL instruction, set operand, instruction 1. And we just put 1, 0, 0 here, and the same for the second operand. It won't be probably in the boot stage, but it will be in the validation stage assembly. Exactly, this is this copy. Here we call, for example, temporary info create, and we put 1 into a 0, So I suppose this is this call, and we pass a global variable to it, and it tries to load the global variable from the stack, but it is of course not on the stack. And it generates a load word instruction, but actually this load operand thing, load operand value, it doesn't generate a load instruction, it generates a move instruction, I think. So we already rewrite it into the load instruction, and we should just add a load address, then it should be fine, I suppose. So here we have a move instruction, and we check whether the operands are pseudo operands. If they are both pseudo, then we generate store word and load word. If only the destination, we will have the case the source is pseudo, and in this case we replace the move instruction with load word. And we already have a variable map here where we look up the second operand. So the lookup that we did here, we can actually just move it, I think. So here we know that the second operand is a global variable. The global variable is the second operand, so we copy it from the from a global variable into a hardware register. So this is the difference between load operand value and just operand value. Load operand value uses a hardware register right away. And the operand that we are interested in is the second operand. And we look it up in the backend symbol table. So the pseudo variable will contain a pseudo symbol, elna RTL object info, or elna RTL type word is a different thing. Elna RTL object info will be the type, that we will have. Or static info. So if this is a global variable, then it will be static info. If it is local variable, it will be object info. So basically our pseudo symbol is what? I'll not tell object info, which is kind of wrong. So I use the counter from this variable, and static info has basically the same layout. Here we can use pseudo symbol as is because they have the same fields basically. So we can check whether the kind, the pseudo symbol, is elna RTL info kind object info, or static info. Then we do something, and here I think that we add an additional instruction. Actually no, source pseudo, destination pseudo, and pseudo symbol. Let us define an additional instruction pointer, an RTL instruction, and call it load instruction. And basically what we have, what we had in this operand value, we need to generate it here. So this load instruction but we do not use the instruction, but we use this load instruction, and we load it into some register. What register do I use here? The register given in the first operand, which actually makes sense, I suppose, because I know that it isn't a pseudo register. So it will be for now a hardware register, meaning that I can just copy the first operand from the instruction operands, and I can do it like this, as it seems. So I can just copy it and pass the kind of the first operand and the value and the length. And then I do not need to append it, or I need to append it, but in the middle I have something like insert, not append but insert, in a list insert, and I pass the instructions here, then instruction, and then load instruction. But I think it inserts the instruction after this instruction, so we still need to swap them. Load instruction. Operand value, operand length is basically auch the same thing as the second operand. So it is just this thing here. Exactly. So it first loads lot word, generates lot word, and then lot address. And we basically should just swap these instructions. So first lot address and then lot word. We can do it by allocating the memory for the new instruction. I definitely already had done this, so probably we just find some place where I already did this. So I generate a store instruction. Yeah, basically I do this with memcpi, where I first allocate an instruction, do memcpi and set it to nil. There was actually a function okay, I probably do not have manual pages in the virtual machine. Okay, we do it with the malloc. Exactly the same we do it here. So basically we will just separate these two cases completely, I think, for now. So I will probably, because they will be also pretty different. So actually here we do then only this, but we also copy this code into this block. And we probably won't need this alloc variable because I already know the register where the value is set. So this will change. Then we need a semicolon here. And well, what we basically do instead of creating this RTL instruction create, we call malloc and allocate the size of an RTL instruction. Then we call memcpi and copy instruction to the lot instruction. And then we set the next value of lot instruction to nil. Now we have a copy and the first instruction, so we still append this lot instruction after the instruction. So lot instruction is lot word, and we need to modify and we need to modify the instruction to be a lot address instruction. Lot address, and the first operand of the, and these are actually the operands, I think. So we remove this stuff here again, and but here we want to use the lot instruction and not the instruction. Let us compile it and see what gets generated. Now we have the lot instruction first and then lot word instruction, and the only remaining thing is that we replace the second argument with the offset from x11. So here we set the second operand to a newly generated pseudo variable, but we want to set it to the first operand of the instruction, so basically to this thing here. So, and it now loads from the x11, but not from an offset. Offset is probably memory. And now everything compiles. If we look into it, it loads the global value first into the register and then loads the value itself in the same register. So we do not need this variable generation anymore. We set just operands to the same values, basically, with the exception that we write here data. Wasn't it data before? Yeah. So and here we replace basically the second operand. Okay, And the function that I was looking for is actually, oh no, it won't work because I copy the instruction here and I overwrite next then anyway with some value that I have to set to nil. Okay, that's fine, I suppose. And now we can remove this no operation, this debug instruction, at least from here. We do not need it here. And we can remove the inert lot operand value. And we can replace it with this second function. Exactly. One more change that I want to do to naming. We have two functions. The one is called operand value and the another one is called load operand value. The difference is that operand value always loads into hardware register, and we probably need to rename the function so that I remember what the function actually does. And this one actually distinguishes between pseudo-mem and pseudo. The load operand value should do the same. Let us rename this inert load operand value into hardware value because it loads the value into a hardware register. Okay, that is done. We can now add the file so that we save our changes. And the last function that still differentiates between static variables or static variables and pseudo registers in the 3-address code or during the generation of assembly is this LNRTL operand value. It gets an TIC operand and then converts it. And here it checks whether a variable is a global variable, and I think that this function is used quite a lot. So to make our work a bit easier, we just copy this function and rename it in the first step. So and I will call its copy just arteleparent value 2, and after migration we can just remove the old version and rename this value 2 version into just value. So to fix the handling here, we have just to remove this branch, I think. We do not need this pseudo symbol variable. Okay, I use it here to see whether it is a byte array or a simple variable. Okay, so we need this one, but we remove this branch, it should still compile. And now we can look what calls can we replace without breaking anything. Probably not this one. This one can be replaced, so that means this is probably the right hand side of a binary operation, and it probably doesn't use global variables. So here we pass the first operand and here the second operand. And the third operand is the target. Okay, let us continue and try other calls. This one is used, the store instruction. Then we have copy to offset. And that's it. So let us already do the renaming, and I think that we just rename this original function rtl operand value. We rename it into value 1, or we can call it something like alt or deprecated probably. Let us rename it into alt. And then we can rename, give this second function the alt name. So these are that instructions. And I think that I generate store word instead of float word. Copy should probably always generate a move. It generates a move if the variable is a pseudo register, otherwise it generates a mem copy instruction. In this case, I check whether pseudo symbol, so the target operand as it seems, exactly the first operand, whether it is a static info, but I never check the source operand. So here I also check the second one, I think. And actually I can shorten it a bit by replacing these two with target operand, and here as well. Actually, in all cases, I check the target operand, but never the source operand. Let us print the source operand. So it will be the second one. We can actually print its kind as well. But we need the name length. And the name. So the kind is register immediate data pseudo memory or pseudomem, but it won't say us whether it is a global local variable. Compiler strings position looks pretty global actually. Yes, for example, this is a global variable. If both of them are pseudo registers, So probably we want to also have a source operand variable to get a copy of the symbol name of the original symbol name from the operand, and we just call memcpi once again and pass the second operand to it, and then we can replace, actually we can replace these two things probably with, so the first one is the target operand, and the first one is the source operand, and I actually want to test it. For that I have to find this copy instruction. So this is actually fine, this is only for debugging. And this is the target operand. This is the this is a source operand. Oh, here I already handle it correctly. So here we know that only the destination is a pseudo, and here we know that only the source is pseudo, so I handle it accordingly. That means that actually the only case that should be handled is the first if condition, if both variables are pseudo symbols. In the case of static variables, so we bring back here this debug code. If the destination is a pseudo symbol, then we add the address of this pseudo symbol in T1, and then we store T0 in this T1, and this one alloc operand, it loads actually the value in the pseudo register into a real register. So if I go to this alloc operand, I wonder, yeah, here are quite a few quite a few places where this function is actually used. I wonder if I can just modify it. Exactly here I check whether it is a pseudo, and then I generate a lot word instruction, but additionally I have to check and it loads it from an offset from the stack. What is the main instruction? We allocate a variable. Actually, this function does the same lookup, and if the variable is already allocated, it just returns the thing. So basically I can check it here. We can probably even put this debug statement here, but I need the operands then. And we will have an else condition. If it is a static, we need to insert two instructions before the current instruction, so load address and load word. Main instruction is the original instruction. Instruction is the last instruction. I think this is the thing. Or is this the first one? Main instruction. Main instruction is the original instruction. It will be the last one. So we copy the original, allocate and copy the original instruction. Then we modify the old instruction to load word. And we set the first operand to register. It is true for load word and for load address as well. So basically we can copy then, and this one is actually also true. We can copy it in here. And this one is true. For both cases. And here we have differences. So if it is a global variable, then we need to load the address first. Why we modify? Oh, here I say what operand I have to set. In the original instruction, it will be actually the same because we have move instruction in this case. So that should be fine. Then we set the load word instruction. This will be also the same, so the first operand will be the same, the second one not. The second one will be in this case RTL kind data. And this value and this length. So this is the value. And this is the length. This is the second operand. And then we can insert this instruction into the list. And actually set it. That won't be enough. Now I need one more instruction. Here are the instructions are already merged. I wonder whether I can just remove this else. That won't be probably enough. Okay, it creates a loop. Because the instruction and main instruction is actually the same. Oh, so we need this code once again for the main instruction, and of course the arguments will be different. So what we actually want to do, we want to allocate one more instruction. We want to copy. I actually do not know. I already know all the operands and I know the instruction that it points to. And the previous instruction, I do not know whether I need to copy it. I can just call instruction create. And this time this will be this load word instruction, and we do not have to copy anything or set the next element. Its operands will be T0 register, but in this case, in the case of the source, it won't be a register, but it will be an offset. I think it is called memory now. Yes. So we can probably remove this one. Do I already have it? I do not think so. Number, register target. Oh, it is this thing from the top. We do not need it here. And this is of course the second operand. And we just need to insert this instruction after the previously generated instruction. This looks about right. So we just create a lot with instruction. This is the target register, and we insert it after the previously created instruction. The return instruction doesn't change actually. Probably I broke something different. No, only this call doesn't compile. I think the instruction order could be probably wrong. So we had a lot with instruction, and we have lot addresses instead. We load it in x5 and then star word and load word, and then we load it into x6, and now we load it load the address, and then we save actually a different thing at this address. Is there different functions? So here we just have different offset. Instruction points to a different thing. Do I use this return value at all anywhere? And alloc operand. Yeah, I do. Basically, we want to return the last instruction in this case. It will be really the main instruction. now it compiles. Okay. Can we reduce the work here somehow? What actually this list insert does? So it takes the existing node. If its last element is nil, then it assigns it the new element, and existing next is assigned to next, and existing next is new. So I cannot append multiple entries. I should do it by one. Yeah, I can kind of revert the order and first generate the load word instruction. I really need a doubly linked list for this stuff. This is too difficult every time to think about it, how to construct a list properly. Main instruction, instruction. Main instruction isn't used after that. That means that we can actually assign this to this result. Result instruction, and in this case we can say that instruction is main instruction and then probably no, doesn't work this way. So instruction is the main instruction, so the last one, and here it would be actually this result instruction. No, actually not. We insert it after the instruction. Oh, because I overwrite the instruction here, I insert it into the wrong place then. But since I do not modify the main instruction here anymore, I can just move the assignment. Yes, this looks better. Now we can move this assignment outside and remove it from this branch. Then we have this list append, and we cannot probably do a lot here. And this is not a result instruction. Yeah. I can call it intermediate or load instruction. Let us call it just load instruction. What do I know? Not perfect, since both instructions are load instructions. So load address and load word, but kind of better than a result instruction, which doesn't tell anything at all about the variable. So now we have this thing, and we had this old function. Okay, we still have one place that should be fixed, but I won't do it today, but probably next time. I want actually to move this debug code. Or at least do this like this, and I can probably move it to this alt function so I can easily find it. This is the only remaining call, yes. Okay, as I said, I try to move the register allocation to a later compiler pass. The pseudo registers earlier in the assembly generation were just local variables, variable in a function, but the assembly generation should handle local and global variables the same and generate pseudo registers out of them, and only on the later stage these pseudo registers should be replaced with appropriate instructions that load values from these pseudo registers into hardware registers. And we almost finished it. Only one function remains, and I will do it next time.